All right, so today is the day that I know everybody's been waiting for, steeped in anticipation for the time that we actually get to start talking about chemical reactions of our organic compounds, all right? And so that's what we're going to talk about today, is these addition reactions of alkenes, our functional group that we're focused on in this chapter. All right, so first of all, both of these reactions that we're going to learn today fall under the category of addition reactions. All right, so what is an addition reaction? If we take our alkene, we're just going to use a very simple one here to illustrate ethene. Okay, we're going to be combining it with some molecule. I'm going to use some variables here. We'll replace these with real atoms here in a second when we talk about our particular reaction. Okay? So what's going to happen is, as we discussed, it's that pi bond in our alkene that really is kind of driving the reactivity of this functional group. Okay? So what happens is that pi bond gets broken. My hydrogens are still here, and it gets replaced with each of those atoms on opposite sides. Right? So we're taking this molecule right here and we're adding it to our alkene. Again, we've broken that pi bond in our alkene and we've replaced it with two single bonds on either carbon. Okay? So this is the general framework for all addition reactions. Okay, so now we're going to learn about two specific addition reactions here. The first one is for a hydrohalogen, HX, where X is one of our large halogens, chlorine, bromine, or iodine. Okay, so again, we're going to take our alkene. We're going to add, let's do HBr. And we're going to be really good about putting our electrons on these structures here. We're going to talk a lot about mechanisms and electron pushing arrows, so we want to make sure that we can see those lone pair electrons as well. All right, so when HBr reacts with an alkene, we have an addition reaction, so our double bond is now a single bond. Still have those two hydrogens on each carbon, but now to one side we have added that new hydrogen, and on the other side that bromine atom. Okay, so to be clear, this hydrogen in HBr is now one of my new carbon-hydrogen bonds, and my bromine in HBr is now added to the other side. All right, so I have an addition reaction with that hydrohalogen, in this case HBr. Okay, and this is a very normal way to look at chemical reactions using this chemical equation here. This is sort of what you would have been introduced to in general chemistry as well, having your reactants on one side and your products on the other side. Okay? In organic chemistry, another common way to write these reactions here is to only have your organic, what we call the substrate, on one side, and then your inorganic reactant we call the reagent. And then finally we have our product as well. So this is another very normal way that things are organized. Chemical reactions are organized or illustrated in organic chemistry. You have your organic molecule, we call the substrate, on the left. You have your reagent that's sort of sitting above your reaction arrow here. That's your inorganic reactant. And then you have your product of your reaction on the right-hand side. Okay? This is kind of the most basic piece of information that I could ask you about a chemical reaction. For every chemical reaction we learn, you're going to have to know the substrate, reagent, and product combinations. Right? By that I mean if I give you a substrate and a reagent, can you tell me what the product is? If I give you the product and a reagent, can you tell me what substrate you had to start with to get there? Right? The combination of these three things, what I call the substrate, reagent, product combination, that's the most basic piece of information that we can know about a reaction. Okay? There are some reactions that we're going to study that's the only thing we got to know about them. And then there are other reactions, like the ones we're going to learn today, where we're going to do a little bit more of a deep dive on that reaction. We're going to talk about the mechanism, the electron pushing arrows, and all that jazz, okay? But again, most basic piece of information we should know about a reaction here. Substrate, reagent, and product combinations, okay? So here's our first reaction of alkenes, the addition of a hydrohalogen. All right, the second reaction we're going to learn about is, again, an addition reaction, but of a diatomic halogen. So again, X is going to be chlorine, bromine, or iodine. If you remember from general chemistry, those halogens are diatomic, so in nature they're always found in pairs. Okay, so again, just to illustrate this, kind of going to keep them here. Now we have not a hydrohalogen, but diatomic bromine. All right, everybody take a second and predict the products of this reaction for me. The product of this reaction for me. All right, so my product is very similar to in the previous reaction, except for now it's not H in Br being added, but bromine being added to both sides of that double bond. All right, so to be clear, in my reagent here, one of these bromines is added to one of these carbons, and the other bromine is added to the other carbon. All right, so we're going to do a little bit of a deeper dive on these particular reactions here. All right, so talking further about these addition of hydrohalogen reactions. We did in our first example this very simple alkene with only 2 carbons. What if I add one more on there and we do our addition reaction with propene? We'll use a different halogen this time. All right, I know I'm going to add these atoms to either side of this double bond, so I'm going to label one of those carbons in orange and one of those carbons in green. Right? One's going to have a new bond. They're both going to have a new single bond. Okay? But in this case here, I would get different products depending on where I added my hydrogen and where I added my chlorine. Right? If I add the chlorine to the orange carbon and the hydrogen to the green carbon, I'm going to get a different product than if I had these swapped. If I added my hydrogen to my orange carbon and my chlorine to my green carbon, right? These would be 2 different products that I would get for this reaction. okay? Now, it turns out that only one of these two products is actually going to be formed. We will not see the chlorine added to that first carbon, added to that green carbon, sorry. The only product that we will see in this reaction here is that chlorine being added to the orange carbon, okay? So why is that? So you guys are just going to trust me for now on that. That is the product of this reaction, okay? So in order to understand why that is, we got to learn a little bit more about the reaction. We got to learn the mechanism of this reaction here. Our mechanisms are going to use those electron pushing arrows to show the movement of electrons and any intermediates in our reaction. All right, so this is why we had to learn all those electron pushing arrows. That's why we did all that at the beginning, is because we're going to study certain reactions and we're going to study the mechanism of those reactions. And the mechanism is how those electrons are moving during that reaction. Okay? The mechanism is like the holy grail piece of information that you could learn about a reaction. All right? It's like the most detail that you could use to talk about a reaction. If you think about it from a laboratory standpoint, it's simple enough to take this and mix it with this and identify what you get out the other side, right? Mixing this with this and seeing what's produced, that's easy enough to do in the lab, okay? Understanding why that one product is produced, why we only get one of those two products, that's now a next level of information. That's now more detail. Mechanisms are often much more complicated to get to in organic chemistry for a chemical reaction, all right? For certain reactions, we're going to learn the mechanism. We're going to use that to help us explain, in this case, why we get only one of these two products. All right? There are other reactions that we're not going to learn the mechanism for. Either it's too complicated or, quite frankly, we don't really know what it is yet. All right? So, but there are certain ones that we do, and these two here are going to be one of them. So, you're just going to trust me that this is the mechanism of this reaction for now. All right? Who did I do? Chlorine? Sure. All right. So let's first play our spot the difference game here. What bonds are being broken in my reaction? So let's just list them here. We got bonds broken. Who can spy a bond that's going to be broken in this reaction? The double bond, so specifically that pi bond in my alkene. Any other bonds being broken? The hydrogen and chlorine, absolutely, right? So this one's also going to be broken. What new bonds are being formed in this reaction? My single bond between my carbon and chlorine, as well as my single bond between my hydrogen and my carbon. Right? So my two new addition bonds there. So in our mechanism, we're going to illustrate those bonds being broken and those new bonds being formed. Okay? But importantly, this reaction here does have an intermediate, meaning that it occurs not just in one step, but in two. All right? So the first step here is going to be our pi bond reaching out and grabbing this hydrogen. First of all, what do we know about HCl? Like, what is it? An acid, a strong acid, right? And so absolutely, that's what it's going to be doing here, is donating that proton, right? It's going to get rid of that proton. And in particular, it's the double bond that's accepting that proton, right? So that pi bond's going to reach out and snatch that hydrogen away from that chlorine atom. All right, so this will produce an intermediate. Okay, so first of all, this arrow here represents what? Bond breaking, bond formation, or both? So this is a both one, right? So not only did I break that pi bond, but I also formed a new bond with our hydrogen. Okay, and then that chlorine became a chloride ion when it accepted that pair of electrons. All right, and there's something very important missing from this mechanism here, from my intermediates here. What is that? The charge, absolutely right. So my charges aren't balanced. I have a net charge of 0 on the left and a net charge of negative on the right, right? So there's got to be a positive charge in there somewhere. And remember, when this pair of electrons in my double bond, when it reaches out to form a new bond with that hydrogen, it got snatched away from that carbon, leaving it with only 3 bonds or a positive charge. All right, so this reaction has a carbocation intermediate. All right, and we're going to see this carbocation intermediate is really important. It's really important in understanding this reaction. All right, so then given what we said our product for this reaction was, I want you guys to fill in the missing electron pushing arrows from that intermediate step there. How do we close out this reaction mechanism? So I need to do now just one arrow, one bond formation arrow, starting at that chlorine and ending at that positive charge. Okay, now, so importantly, just by looking at this reaction here, I know I uglied it up with a lot of colors, but it wouldn't be possible to know the mechanism just by looking at the reaction, because it wouldn't be possible to know that it happens in 2 steps, right? That we get this carbocation intermediate. So this took a lot of research to find that indeed this reaction occurs in 2 steps and that there's this carbocation intermediate. And that's going to be really important in understanding why there's only one product here. Okay? So in order to understand why that is, we got to talk about the stability of carbocations. All right, so first of all, we have this classification for carbons. We have, if a carbon doesn't have any carbon neighbors, as in this case here, we would call this a methyl carbon. All right, if we're looking at a carbon, for example, this one highlighted in blue here, and it has 1 carbon neighbor, we call this a primary carbon. If we have a carbon like this one here, highlighting in blue, in the middle, that has 2 carbon neighbors, right? 1, 2. This would be a secondary carbon. All right, and lastly, we have a carbon like this one here with 3 neighbors, 3 carbon neighbors, 1, 2, 3. This is what we call a tertiary carbon. There are also quaternary carbons, although they're not going to pertain to what I'm talking about here in a second. Okay, so we have this classification system for carbons depending on how many carbon neighbors it has. If it doesn't have any, it's a methyl carbon. If it has 1, it's primary, 2 is secondary, 3 is tertiary. Okay? Well, if we take these carbons here, these tertiary, primary, secondary, methyl, and we form a carbocation, these carbocations have different stabilities. Okay? It turns out that the least stable is a methyl carbocation, and it goes in order from there. So the next least stable is a primary, a secondary is more stable, and finally the most stable carbocation that you can have is a carbocation that forms on a tertiary carbon. All right, so let's look at our mechanism again. I have my alkene. And my hydrohalogen. That first step is that double bond reaching out and grabbing that acidic hydrogen and breaking that hydrogen-chlorine bond. Okay? But just looking at this mechanism here could sort of go one of two ways. I could have that new bond be formed between hydrogen and carbon right here, and thus have this carbocation. Or I can have my new hydrogen-carbon bond over here and have this carbocation. All right, depending on which carbocation formed, I would get different products, right? If I took the path on the top, I would get this product, where the chlorine is on that very first carbon and the hydrogen is on the second carbon. Okay, or if I had my other one, finish off this mechanism, I would get a different product where my hydrogen is on carbon 1 and my chlorine is on carbon 2. Okay, so which path is this mechanism going to want to take? Which path is this reaction going to take? The top one or the bottom one? Why the bottom one? Because of my intermediates, right? Because here I have a primary carbocation, and here I have a secondary carbocation. Right? So a carbocation on a primary carbon is not going to form, which is why I only get one product of this reaction here. Okay? So to be clear, looking at these products here, there's no difference in the stability of the products. The chlorine's perfectly happy to be on the first carbon or the second carbon, right? So just looking at those two endpoint molecules, I can't decide what's more stable, right? The difference is the intermediate in the reaction, the path that's being taken, and the fact that you have a more stable carbocation on a secondary carbon, on a more substituted carbon, than you do on a less substituted carbon. Okay, so it's our intermediate in this reaction, that carbocation that's giving us just that one specific product. Okay, so the fact that we get one specific product here is what we call a regioselective reaction. We get our new carbon-halogen bond, We'll just say our new bond. On a very specific region of our molecule. All right, so this reaction is selective as to where that chlorine gets placed. We call those types of reactions a regioselective reaction. We don't get every possible product that we can draw here, right? We specifically get that halogen on that more substituted carbon. Okay, so this is a regioselective reaction, and in particular, our new carbon halogen bond is on the more substituted carbon. All right, it's going to form on that secondary carbon because that forms the more stable secondary carbocation. All right, and this type of regioselectivity, where it goes on the more substituted carbon, is what's called a Markovnikov type reaction. Obviously named after some Russian dude who established it. Okay, so this is a reaction, and we're going to learn a bunch of reactions that are regioselective. We get one particular product out of it because of the region in which the new bond is formed. This specific type of regioselectivity, where it's formed on the more substituted carbon, has a special name. It's a Markovnikov reaction. All right, so before we move on here, let's go ahead and do some substrate reagent product examples here. I'm going to put down some substrates and reagents and products, and you're going to fill in what's missing. Oh, that's not what I meant. All right, so let's look here. We're going to have an addition reaction where our atoms get added to either side of this double bond here. Where is my halogen going to go? On the red carbon or the blue carbon? Which one is it? The blue one, right? Because this red one is a primary carbon. The blue one is a secondary carbon, right? So that carbocation will want to form on the more highly substituted carbon, which is then where my iodine is going to go. Okay? My hydrogen will then be added to the less substituted carbon. All right, so now for this one, I gave you the product, and I'm asking you for what alkene would be used to form that product in this reaction. All right, now, if we go back to this first example here, I explicitly drew in that hydrogen on that red carbon, right? That was kind of being nice, though, because, of course, we don't draw our hydrogens explicitly, right? So not having that hydrogen explicitly drawn, just having it be implied, would be a perfectly reasonable way to draw the product of that reaction. So down here, there's no explicit hydrogen drawn, so I can't figure out just by looking at it where that double bond is going to be. All I know is that it involves that carbon right there, right? So I got two possibilities here for my alkene. One where the double bond is formed between carbons 1 and 2. All right. Or the other would be if it's formed between carbons 1 and 3, or 2 and 3. All right. Both of these are alkenes that involve that blue carbon right there. But only one of them would actually give me the product that I see here. So let's see, A or B. Who thinks we should use alkene A? And who thinks B? So it's going to be A, because again, the halogen is going to go on the more substituted carbon, right? So this is a primary versus a secondary. But in B, we're looking at a secondary versus a tertiary carbon. So B, my halogen would be added to the green carbon, and that's not my product. All right, so in this case, I can narrow down what my alkene was to this, whatever, 3-methyl-1-butene. Okay, so then for the last one here, again, I'm going to add my halogen to one of these two carbons. All right, what is the blue carbon? Primary, secondary, or tertiary? Secondary. What is the red carbon? Primary, secondary, or tertiary? Also secondary. So where is the bromine going to go? Is it going to prefer one of these carbons over the other? No. And so in this case here, we have to draw both of our products, right? Our mechanism, our regioselectivity is for the more highly substituted carbon. One of these carbons is not more substituted than the other, so there's no preference considering our mechanism. And so instead we have to draw both products. One where it's connected to the red carbon, and one where it's connected to the blue carbon, right? I had a tie in terms of what was more highly substituted. Okay, and again, you could draw the hydrogen on the other carbon, but you don't have to because hydrogens are implied. That's perfectly legal. Okay? So again, we have this reaction here that is a Markovnikov reaction, meaning that it's going to prefer the more highly substituted carbon. But if we have an alkene where both carbons are equal in their substitution, you will get a mixture of both of those products. All right. So there's one more consequence of this mechanism that we studied, this carbocation intermediate, and that is what's called a hydride shift. This is kind of a special circumstance that we got to be careful for and got to watch out for. It doesn't happen all the time, but it will happen in specific molecules. So let's take this alkene here. We mix this with HCl. This is the reaction that we just looked at. We would predict our product to have the halogen on the more substituted carbon from my alkene. This one right here. All right, now, if you mix these two, you will get this product, but it's actually going to be the minor product in this reaction. All right, you will get a different major product, and this major product is the result of what's called a hydride shift. All right, so in order to see that, we got to actually go through and draw our mechanism here. Okay, we can illustrate this hydride shift with our electron pushing arrows. All right, so that very first step is the same as it always is. That double bond reaches out, grabs that hydrogen, breaks that hydrogen-chlorine bond. All right, as we would expect, that hydrogen is bound to the less substituted carbon so that our carbocation can form more stably on the more substituted carbon. Okay? This carbocation carbon right here, what is this? Primary, secondary, or tertiary? Secondary. And what is it located to right next door? This carbon is what? Primary, secondary, or tertiary? Tertiary. And wouldn't that carbocation just love to be on that tertiary carbon because it's much more stable on a tertiary carbon? And so that's what we're going to see. We're going to see this carbocation kind of jump over to its neighbor so it can form that more stable carbocation, that more stable tertiary carbocation. Okay? Now, the carbocation itself is a positive charge. It can't do any moving. The only thing we can move are electrons. So what actually jumps in this reaction here is the hydrogen that's on that tertiary carbon. It's just literally going to jump over to that carbon there. All right, and this will leave us with a tertiary carbocation. All right, so this right here is my hydride shift. That hydrogen with its pair of electrons jumping over to that neighboring carbon so that that more stable carbocation intermediate can be formed. All right, I got a little lazy and didn't put in my chloride ion, so let me put that in. All right, so then my last step here would be the same. That chloride ion finds that carbocation and forms that new bond. So everybody take a second and draw me the major product of this reaction here that's a result of this hydride shift mechanism. right, now, if you remember, one of the things that I had said is like a good double check is counting carbons. Now that we're doing reactions, that's a really good way to make sure to double check that you don't have any missing carbons, right? We are not rearranging the carbons whatsoever, right? I should still have branch points where I have branch points, still have the same number of carbons, all that jazz. So if you're having trouble drawing your products, you basically want to start with the framework of your alkene. Nothing's going to change in terms of what's bound to what here. All we want to do is add that new bond to my chlorine. So again, this will be my major product. If you drew it in this sort of like kinked way where you just kind of, you know, inserted in there that new bond, that's fine. I understand that it makes it much easier to see like, okay, I started with this and I ended with this plus that chlorine, right? Kind of visually makes it easier to see what's going on. If we were being really good, we would space these bonds out 90 degrees from one another because we have 4 bonds there, okay? But I'm perfectly fine if you want to leave it all sort of kinked so that it's easier to see where things are going. I'll allow it, all right? Cool. So because of my alkene, we actually get our major product is our hydride shift product here, okay? And be careful on your homework, I'm going to ask you specifically for your major products. So you need to be on the lookout for this possibility of this hydride shift that can occur, right? So why, looking at my molecule, let me get rid of all this blue here. Why did I know that there was going to be this hydride shift that occurred? Right? Because I had a secondary carbocation right next door to a tertiary carbon. Right? So that's what we got to be on the lookout for. Is our carbocation is going to form on this secondary carbon here, but that's right next door to a tertiary carbon. Right? So that's how we're going to spy that these hydride shifts occur. It obviously isn't for all alkenes, but you do got to be able to recognize the alkenes that will have a hydride shift major product. All right. So let's move on to the next one here. Our last reaction was now our second reaction was the addition of a diatomic halogen, right? Chlorine, bromine, or iodine. All right, these 3 are always grouped together, and notice what isn't in there. Fluorine, the very first halogen there, is always kind of left off. It doesn't behave quite the same as the rest of them because it's so teeny tiny and electronegative. Okay. All right, so now we're going to take a look at the mechanism for this reaction here. All right, so actually if we just take a second and draw our products for this reaction. Notice that because we're talking about this diatomic halogen, I'm adding the same thing to both carbons, right? I'm adding a bromine to one side and a bromine to another side. So this reaction here is not regioselective. It's not like it prefers one side or the other because you're adding the same thing to both sides. So we don't have this same thing to worry about, this same regioselectivity concern. Okay? Don't worry, we do have to complicate it a little bit though. All right, so let's look at the mechanism of this reaction. All right, again, that first step is very similar. We have our double bond reaching out. Now it's going to form a new bond with bromine. That breaks that bromine-bromine single bond. Okay? But there's one more arrow in this first step here, and this is kind of weird, but bear with me here. It turns out that that bromine does not like being attacked. It's not very happy about it. So it's going to fight back, and its pair of electrons is going to reach out and form a new bond with that carbon. And so what we get is a cyclic intermediate, where the bromine is bound to both carbons. All right? Because of this, now this halogen has two bonds and two lone pairs, leaving it with a positive formal charge. And I also have my negatively charged bromide ion in there as well, right? So I still have my charge conservation in this step. Okay, so this mechanism is characterized by this cyclic intermediate. And there are some interesting consequences to this that we'll see in a second here. All right, so just to be clear, just to sort of illustrate this a little bit better, right? Remember this first arrow that I drew is that bond breaking and formation arrow. So this bond is going to break and form a new bond with that bromine here, right? So this arrow represents the formation of this bond in my triangle. But again, that bromine kind of fights back, and its pair of electrons will also reach down and form a new bond with that neighboring carbon, right? So these sort of cyclic moving arrows here is how I get my two new bonds to my bromine from my alkene. And then I have my normal old bond breaking arrow leaving me with a bromide ion. All right, so then from here, how do we get to our products? All right, that bromide ion is going to go ahead and attack one of those carbons, and that breaks that triangle open. Okay, so again, this mechanism is characterized by this cyclic intermediate here, where I have this positively charged halogen bound to both carbons on either side of my, what used to be my double bond. All right, so what are the consequences of this mechanism here? Well, let's just look at another alkene. We're going to use a cyclic alkene. Okay, for the sake of variety, I'm just going to use a different halogen. So that first step is that pair of electrons reaching out and grabbing that chlorine, that pi bond. But again, that halogen's going to fight back and form that cyclic intermediate. Okay, so I'm going to try to draw this in such a way where I'm kind of like looking at the side view of this intermediate here. So I'm going to take this ring and kind of flip it on its side. All right. If I'm forming a triangle, am I going to be able to form a triangle where one bond's above the ring and the other one's below the ring, or do they both have to be on the same side? They're going to both have to be on that same side, right? So I'm going to have this cyclic intermediate form on one side of that ring. Okay? And because of that, because that cyclic intermediate is on that one side, it's blocking that chlorine from being able to approach from that side. Chlorine can't get to it from that side because that triangle is in the way. All right? So instead, the only way for that new chlorine to be added to this ring here is to add to the opposite side, to attack the carbon from the back side. All right, the side where the triangle has not been formed. Okay, and again, this bond will break onto that carbon. So because of that, I have one chlorine on one side and one chlorine on the other side. All right, and we have a special name for that in terms of our stereochemistry for our cyclic alkanes. All right, what do we call it if one bond is pointing on one side and the other one on the other side? This would be the trans isomer that forms. Okay. We get one specific stereoisomer out of this reaction. This is what's called a stereo-specific reaction. So it's not regio-specific like the other one, but it is a stereo-specific reaction. Our product has a specific stereochemistry. All right, I get no cis product. All right, and again, the reason for this stereospecificity is that those chlorines have to be added to opposite sides of my double bond. This is what we call an anti-addition. All right, so our addition of our diatomic halogen is not a regio-specific reaction, but it is a stereo-specific reaction because of the way that those two atoms are being added, and they're being added to opposite sides of that double bond, what we call an anti-addition. All right, now there's one more thing we got to be good about here. For this product here, is this a meso compound? It is not a meso compound, right? If it was the cis isomer, it would be, but it's not. So this is not a meso compound, which means I also have to include its enantiomer, right? Since these are two distinct molecules here, I'm going to have to include them both. So we have to include both of the trans isomers as our products here. And since it's a stereo-specific reaction, we have to use our dashes and our wedges to show the stereochemistry of that product. Cool. All right. Notice how this wasn't a consequence up here because I didn't generate those two new stereocenters. All right, but when I have my ring here, I had to worry about it. All right, so now I'm just going to put down a mixture of problems for our reactions that we just studied here, and you're going to fill in that missing information. Okay? All right, so for this first one, we have to be mindful of the fact that this is that diatomic halogen iodine being added in an anti-addition. So one of those iodines is going to be added to one side of the ring. The other one will be added to the opposite side of the ring. Okay, but again, we got to be good because this is not a meso compound, so it's an enantiomer will also be produced, or I just got to swap those dashes and wedges, right? These are two distinct molecules. All right, so for my next one here, this is a hydrohalogen addition reaction. I know based on my product that this carbon right here is going to be involved in my double bond, but it could be any of these other ones here that are also in that double bond. Okay, so if I just want to like draw out all the possibilities here, let's just color these carbons. So we got a red one, an orange one, and a green one. So here was on the red. Let me make some room for myself. We'll do another one. Where it's on the orange. And then another one where it's on the green. All right, so let me just finish coloring. So this one in the middle was the blue. All right, so if I started out with this top one here, would this give me my product that I desire? Would I get the chlorine added to the blue carbon, to the more substituted carbon? Let's take a vote. Who thinks yes? Who thinks no? Oh my gosh. All right, y'all. Holy hell. So if we have this right here, this carbon is a primary carbon. This is a secondary carbon. So indeed, I would get my product where the halogen is being added to that more substituted carbon, my blue carbon. So check, check. This one works. What about this one here? Let's focus on this structure. Would this give me my desired product? Right, my blue is, oh my gosh, I'm sorry, it wasn't secondary, it's tertiary. My blue is tertiary, my orange is primary. Okay, so this would also work. All right, but if you try to include both of these, I would ding you for it. Why is that? Are they E and Z though? Let's be careful. If they were E and Z, we'd have to include them both. But are these two different stereoisomers? They are the exact same molecule. All right, so if you try to give me both of them, I'd have to ding you for it. These are two identical molecules, okay? Because this is not a, that carbon is bound to two hydrogens. These are two identical molecules just flipped around. I'm going to get rid of one of them. All right, so now my next one here, if we started out with this alkene, would we get our product that we want? This is a secondary carbon. My blue one's a tertiary carbon. Yeah, and these are indeed distinct molecules, So either one of those can be used to generate my product here. All right, and then lastly, for this one here, I'm going to start out with my same carbon backbone here. I'm going to put my bromine on that more substituted carbon, and I'm done. Is this the major product of this reaction? No, why not? Because of the hydride shift, absolutely. So this one right here would be considered a minor product. My major product, because I have this secondary carbocation that's going to form directly next to a tertiary carbon, I'm going to have that hydride shift. All right, and so my major product is going to have that bromine on that tertiary carbon. All right, so major is that hydride shift product. Yeah?
So for that first example you showed with the two iodines,
Yeah.
there would be no minor or major product even if there's a tertiary?
There's going to be a perfectly even mix between the two, because in this case, this doesn't go through a carbocation intermediate. These mechanisms here have no chance for a hydride shift because it has that cyclic intermediate. So we don't have to worry about hydride shifts with this particular reaction. We only have to be on the lookout for them when we're using a hydrohalogen, because those specifically go through that mechanism with the carbocation. And that's why you get a hydride shift, is because of the carbocation, right? So these ones up here, we don't have to worry about any hydride shift for. All we got to worry about for these reactions is that stereospecificity, the fact that these two get added on opposite sides. Cool? All right. All right, so